So my talk is very much at this intersection. It's joint work with Mert Palanchi. He's now at Stanford. He was a student with me. All right, so what's the broader motivation here? Well, the broader motivation is that the size of data sets that we're working with these days are just growing and growing and growing. This is the so-called big data phenomenon. So it's driven by technology, the internet, and so on. And this is a plot from IBM, for instance, just showing with not quantitatively labeled axes, is showing exponential rates of growth in the amount of data that we're collecting. All right, but of course, as statisticians, we know that data on its own is somehow not interesting. Data is only interesting as a lens to understanding things about the world, about physics or biology or sociology and so on. We need to do inference, and many inferential procedures involve optimization. And so what's interesting with very large data sets is that things in statistics and optimization that are actually very simple from a classical point of view, even things as simple as just doing a linear regression, solving least squares equations, these can become relatively expensive when we're dealing with data sets that are of this magnitude. So that forces us to sort of revisit things, revisit optimization problems that at one level you could say are solved because they're already polynomial time. We know how to solve them in poly time, but we can revisit them and see if we can solve them much more quickly so that our methods really scale up to large problems. All right, so now I think the mic is working. So some people missed the intro, sorry about that. Okay, so the high-level picture here is that very large data sets need fast algorithms, but at the same time, in this talk, I want to emphasize methods for which we have rigorous guarantees. Of course, you can do many heuristic things to speed up algorithms and so on, but we'd like speed-ups, but at the same time, we want some sort of fundamental understanding of what we can expect from the methods. And this talk is really just about the application of an idea that's not new, and it's in some ways an embarrassingly simple idea. It goes under different names. It's known as randomized projection. It's also known as sketching or data sketching. And it's very simple. The idea just is that if you have data that lies in some high-dimensional space, for instance here, one way to reduce dimension is just to choose a random subspace. You can think about this as choosing a random matrix, and we'll talk about the random matrices in a minute, and doing a multiply. You just take the data and you project it down to a much lower dimensional space. Okay, so it seems very naive. It's naive in some ways because the projection is data oblivious. You're not looking at the data before you project it. Something like PCA is a projection, but it's looking at the data to find out a good projection. This is data oblivious. So you might say, well, that's crazy, it's not going to work. But in some ways, data obliviousness is good. We're going to see that it's very cheap to do these projections. You don't have to solve eigensystems. You just do matrix multiplies. And we'll also see that we're going to be able to get guarantees that are pretty uniform. They don't depend on the particular structure of the data that you're operating on. All right, so as I said, this is not a new idea. It goes back at least to the work of Johnson and Lindenstrauss, who weren't really interested in algorithms or applications in any sense. They were Banach space theorists who were interested in studying the geometry of Hilbert and Banach spaces, and they realized that they could use the probabilistic method, essentially taking random slices or projections of spaces. They could learn interesting things about the geometry of certain kinds of function spaces. The computer scientists, of course, picked up on this for algorithmic reasons, and it's now widely used. Many different algorithms have been studied and how they can be sped up with this idea. There's various nice surveys and books, one by Vampala. Mahoney and his colleagues have a nice survey paper, and Kermode et al., among others. All right, so this will be our basic building block. And the questions that we need to ask, and we're going to flesh out as we move forward, are how do we do random projection? What are good matrices? I actually won't spend that much time in this talk on that question. One could give an entire talk about the construction of good matrices for this purpose. People often call these matrices JL matrices, JL for Johnson-Lindenstrauss. This is named after a lemma that has their name, the Johnson-Lindenstrauss lemma. So I'll talk a little bit about that, but not so much. What I will talk about a lot more is how large, or conversely, how small can we make this projection dimension while still preserving useful information about the high-dimensional space. And that's what various people address in this literature, and I'm going to do this in the context of a certain class of convex optimization problems here. All right, so let me introduce this idea of randomized projection or sketching. These are essentially the same names, different names for the same thing. Let's introduce this idea for optimization. And it's useful to sort of compare, contrast with distributed optimization, just to understand the big picture. So in modern optimization with data, we typically have data sets that are so large that we could never store them at a central site, right? And so there's different strategies for dealing with this. What a distributed optimization procedure would do would be, well, we might have multiple processors, or we might send data to the centralized processors. We might take a subset of our data, subsample it, and send it here. And the way we can think about optimization, so in optimization, where do these come? We're trying to fit something. We might be solving a maximum likelihood problem, some other optimization problem suggested by the data. If we had all the data, then we would get some cost function that looks like this, right? And we're trying to find the minimum of it. If we just use a snapshot of our data, we're getting sort of a noisy approximation to that cost function. And so we could imagine minimizing it or computing the gradient of this function and using that in some iterative update. If we took the gradient step, that would be like a block stochastic gradient method. Okay, so these are distributed approaches. What sketching does is, well, a distributed approach might iterate. I then might take data from another subset of data and transmit it, and so on. The kinds of sketches that we're going to be looking at in general, when you do sketching like that, when you subsample data, those are called subsampling sketches. And you can prove things about them, and I'll mention when we can. But there's actually a much broader family of sketching techniques, much broader than just subsampling sketches. The general picture that you should have in mind is that what you can do is you can have some weights that apply to all of the data sets simultaneously, and you take a linear combination and you send a sort of synthetic data set. It's not a subsample necessarily, but it's some kind of random combination of your original data set. You send that synthetic data set to the optimizer, and what we'll see in many cases is that you can prove much stronger things about the approximation that you get from this synthetic data set. Okay, so that's the idea of sketching. Sketching is going to create sketches. Think of those as synthetic data sets that are much smaller than your original data set, but still summarize, contain information that's useful, and will make this precise as we move forward. All right, so to make these pictures a little more concrete, let's warm up with a relatively easier class of problems. It's relatively easy, but it's still of immense practical interest. So what's the problem? We've got a data matrix A that's n by d. Throughout the talk, n is going to be the sample size, the number of samples. D is the dimension of your problem. You have a response vector y, and you might have a convex constraint set C. And what you'd like to do is compute the constrained least squares estimate, minimize the 2 norms squared of ax minus y, subject to the constraint that x is in this set C. Okay, so if C is R to the D, this is just least squares. It's possibly one of the most widely solved problems in scientific computation. But in modern data analysis, we often have regularization or constraints. If we wanted sparsity in our vector, we would have something that involved an L1 constraint in C. If we had a matrix problem and we wanted to enforce low rank structure, we might have something like a nuclear norm that defines C. So often we have side information about the structure of the solution that we expect, and that can be encoded by a judicious choice of this set C. All right, so what does sketching do for this problem? Okay, so we have a data matrix. Throughout this talk, I want you to think about this regime, a regime where n is large relative to d, n is the sample size. And we're choosing a random matrix S, and we're constructing a synthetic data set with this matrix multiply. Okay, and using that synthetic data set, we can define a randomized approximation. This is a new objective function. Even conditioned on the data, even with a and x fixed, it's random because the sketch is random. And so we're going to solve this problem. We're going to get a random vector x hat, and we want to understand how close x hat is to x least squares. Okay, so that's the basic idea. As I said, this idea is not new. I think one of the first analyses of it was a paper due to Sarlos. But most of the past work is focused on the unconstrained case. We're going to analyze it a little more generally for any convex constraint set C. All right, so there's many issues. How do you choose these matrices? The kind of theory that we give at some level is not specific to particular S's. What our theory says is that if you give me an S that has certain properties, we can call them S's that are good in some sense, then your optimization method will have good guarantees. And so what are examples of good S's? The easiest one to analyze is if you just make S have IID Gaussian entries. That will satisfy the criteria of the theory that I'll present in a moment. In practice, that's not such a good choice, because now you have a dense matrix, and you're telling me that you should multiply a dense matrix with another generically dense matrix. That's going to be expensive. It could be the case that the cost of projecting the data, of sketching the data, is more expensive than the cost of solving the original problem. If that were the case, then your method's not practically interesting. But as I said, there's a huge literature on Johnson-Lindenstrauss type matrices, JL matrices. There are what are called fast JL matrices. There are what are called sparse JL matrices. So I won't get into the detail of them, but at high level, they are all clever constructions of random matrices for which you can do the multiply very, very quickly. For instance, if you make a matrix that has a ton of zeros, then the multiply is much faster, right? You're going to pay only the price for the non-zero entries in S. That's what a sparse JL transform does. But these matrices are random, they're structured random, and they still have good properties, and our theory will apply to them. The last type of matrix that our theory also can apply to is when you have matrices that are partial identity matrices. That's just a fancy way of saying that this matrix selects a random subset of the rows of A. Our theory also applies to those, but for such matrices, you end up needing stronger conditions on things like the leverage scores of A. For the other sketches I talk about, we don't have those kinds of constraints on A. Okay, so that's the basic idea. And so what can you show about this method, right? So what you'd like to show is you'd like to show that if I choose S in a certain way, and what's really very relevant here is how large M is. You want M to be small. Right? If you make M very large, you're not reducing dimension in an interesting way. So you want M to be as small as possible while still retaining some guarantee about how close x hat is to x least squares. Okay, so that's the game that we'll play. Now, when you have optimization problems, there are different ways, of course, of measuring the accuracy of an approximation. Here I'll start with one. Later I'll talk about another one. But one way of studying accuracy, so this is a randomized approximation, and we can say it's delta accurate in cost if, when you compare its cost to the optimal solution, that's the true minimizer, it's at most 1 plus delta optimal. Okay, so delta is a tolerance parameter, something, let's say, between 0 and 1 typically would be a choice. All right, so here's a theorem. It's a little vaguely stated, but I can flesh it out. So it says, for a broad class of random projection matrices, I gave you some examples as I was discussing before. If you choose the sketch dimension to be larger than something we call the effective rank of the data matrix with respect to the constraint set over delta, then you will have this guarantee with exponentially high probability in M. Okay, so what is effective rank? I'll give you some pictures to give you intuition in a moment, but just suffice to say that if you have an unconstrained problem, if C is R to the D, if you're just sketching least squares, then the effective rank is exactly the rank. The effective rank is always smaller than the rank, can be much, much smaller than the rank, and that's going to happen when we have a certain structure of our solution set C that I'll illustrate in a minute. Okay, so as I said, most past work has been on the unconstrained case, and people have proved results of this type with rank of A, and often there's extra logarithmic factors and so on. Those turn out not to be necessary. This is a sharp result here. And as I said, the effective rank can be much, much smaller. Okay, so let me give you intuition. What is the effective rank? Why is the sketch dimension scaling like this geometric object? Okay, so the way to think about these problems is in terms of if you are sitting at a point, suppose that I had a constraint set that was a polytope, just to illustrate, and that was your least squares solution. Let's just assume that it was at this vertex. Right? If you were sitting there and you were asking yourself, am I optimal or not? Right? What you have to do is you have to check all first order, you have to check all feasible directions from a first order point of view. You have to look in the tangent cone, which is the set of feasible directions pointing into the constraint set. And you have to see, could I descend along any one of those directions? If I could descend, that means my point is not optimal. Okay, so what we're interested in is a randomized approximation that preserves optimality up to a delta tolerance. And so what this picture suggests is that what we actually need to preserve is just this cone of directions. We don't care at all about these directions in general, because they're not relevant to ascertaining optimality. Okay, so the effective rank is exactly a measure of the size of this cone if you cap it. If you make an ice cream cone out of it, and you measure something like its volume in a sense, that defines our effective rank. Now, of course, if you don't have constraints, if C is R to the D, then the tangent cone is not interesting. The tangent cone is the whole space. So in some sense, unconstrained least squares is the hardest thing to sketch because you have the most directions in which you have to certify optimality. Problems that have interesting geometry like this are easier to sketch. That's what our theory says, and when you do experiments, you'll see this effect. To be clear, this notion actually depends not just on the constraint set, it also depends on where your solution is in the constraint set. Because if you moved your solution to a higher dimensional face, you get a very different tangent cone. It's quite larger dimensional, so you're going to need to sketch to a higher dimension. So what our theory actually says is that the sketch dimension depends both on the data matrix A, the geometry of C, and where your solution sits within that set. And that's useful because it means for a lot of problems we can get tremendous speed-ups, much, much faster than the rank. And I'll show you one example in a moment. Okay, so that's a general guarantee in terms of this notion of cost approximation. And until Mert started looking at this problem, as far as we could tell, all past work had looked only at this notion of approximation. And it's a perfectly valid one, it's fine. But certainly if you're a statistician, when you do a linear regression, you often care about details of the fitted vector itself. And so you care something about how close is x hat, or perhaps a x hat, how close is that to a of least squares in some norm? Okay, so that's a different notion because you're guaranteeing not just closeness and cost, but you're saying the solutions are close in some sense, the optimal solutions. Right, so the picture to have in mind is you have your least squares problem here, you have your sketch solution here. Approximate cost is looking at this difference here. It's looking at if I take this point and I plug it into the original problem, how suboptimal is it on the y-axis? Whereas a solution accuracy guarantee is looking at this distance in x space, how far is x star from x hat? Okay, so these things are related. if you're close in cost, you can somehow leverage that with some side conditions to say that you're, perhaps with strong convexity, that you're relatively close in solution. But what we were interested in is if we actually look at practical statistical problems and we use this sketching technique that I've told you about so far, I'll call it the classical sketch, this technique where we just multiply, we do a left projection of the data matrix, we use it once. What happens in practice? This method turns out to fail in a pretty spectacular way, which was surprising us to at first, but once you study it a little more, it becomes clear why it happens. So what we did is the following. We sort of studied how this random sketch behaves if we applied it to problems where the response vector is equal to some AX star plus Gaussian noise. Okay, so that's a very classical ensemble of Gaussian least squares problems. We solve these all the time. So if your method doesn't work for this class of problems, it's a concern. And what we did is, well, what you can do is that if you solved the original problem and you looked at how well the original problem was tracking, how well was it estimating X star, if you had n samples, your mean squared error, you can do a simple calculation, will drop off like rank of A over n. And that's what we're seeing in this plot. What I'm showing you is if I solve the original problem and look at how well it's tracking X star, as a function of sample size, mean squared error, on a log scale, I get a straight line. That's a 1 over n drop-off. Now, what I've done here is I've applied the classical sketch. What my theory told me to do, it's an unconstrained problem, so the theory says use the rank of A. I'm looking at problems where n is always bigger than d, so the rank of A is at most d. So I'm using sketch dimensions that are some constant times the dimension. And the theory tells me that you'll get a good cost approximation, but the simulations show you that you get a terrible solution approximation. There's an error floor in this method. And this is very bad because it means if you solve the least squares problem, it would give you an accuracy to what you're after. That's the inference step, what you're actually trying to estimate. It would give you very high accuracy, something like 10 to the minus 3. Whereas your sketch is terrible. Its error is of the order 0.4, 0.5, something like that. All right, so solution approximation and cost approximation are not the same thing. So when Murch first showed this to me, I was pretty puzzled. At first I thought, oh, you've implemented it incorrectly. And then he convinced me he hadn't. And then we thought, well, maybe we're just not doing the best thing we can do with the sketch. If we do something more clever, we can get a better curve. But then we studied it some more, and here's where information theory is actually useful. You can study this from a fundamental point of view, and you can actually prove that if you just have one sketch, if you only touch your data once, there's no method that can have a curve that's better than this. There's no method that will have a decaying approximation like this. Okay, so that's a fundamentally negative result. It says that there's something flawed from a statistical point of view about just sketching your data once. Now, some people who prove lower bounds, this is sort of an interesting comment on mathematical culture. There's some people who prove lower bounds that are, for them, the lower bound is the ending point. Sort of like a negative assertion. I prove that you cannot do better than this over this entire class of algorithms. I think that's fine, but I think I'm more positively minded. When I see a lower bound, my thinking is, well, the lower bound will tell me how to fix methods or to adjust something in my model or my algorithm design so I get a better method. And that's what actually happened here. We realized, as I've alluded to, is that the lower bound proof would break down if you allowed feedback. So that means if you're allowed to sketch once and look at the results and do something, and then sketch again and do something else in an iterative way, if you iterate this method, the lower bound does not apply. And that led us to a sequential scheme that I'll describe in the rest of the talk. This is a scheme that is using exactly the same number of sketch dimensions as this scheme. So it's a fair comparison, but you can see it's now tracking the optimal solution very well. And we can prove a theorem that tells us why this happens. Okay, so let me just give you an illustration before I sort of dive into more generality. Let me just give you an illustration of the kinds of speedups that this sequential or iterative sketching scheme that we have can give you. Just for fun, we applied it to Netflix data. Netflix data, you have a large data matrix. Your A matrix is a lot of users. Users would be rows, and columns would be movies. And what you're interested in doing is building predictors that sort of figure out how to predict or recommend movies to users. And there's a whole area of machine learning statistics devoted to exactly this problem, collaborative filtering recommender systems, that's what this is called. I don't want to dive into the full goriness of that, but let me just sort of show you if you do one naive thing. This is something that people do in practice. What they do is they take their data matrix and they hold out one column. So they're holding out one movie, and then they're trying to use all the other columns to do a linear regression, try to use all the other movies to predict the ratings of one held out column. They often put a penalty, a kind of what's called a ridge penalty in statistics. It just means a squared L2 norm penalty. Okay, so it's an instance of our class of problems. We have a regularization as well, but that's a minor tweak. What they actually want to do is solve this class of problems for a whole range of lambda. At the end of the day, of course, in statistics, we always partition our data into a test and a training set. We fit on a test and we evaluate on training. So they want to do that as well. They'd like to choose the optimal lambda. Okay, so you'd actually like to solve a sequence of least squares problems. So what I'm showing you here is the test error that you achieve, and I'm showing you as a function of lambda. So you're computing the whole path of solutions. And what I'm showing you in blue here is what you would get if you use a direct method. Use a Cholesky solver, which actually computes a Cholesky factorization. Okay, so that's very stable because it's a direct method, and we can take that as ground truth. What in practice you're more likely to do is you would start using iterative methods. Something like conjugate gradient is a standard iterative least squares solver. There's many versions of CG, but if you choose a version, so the original direct method takes 1700 seconds. We chose a version that roughly halves your computation time. It's twice as fast, but you can see it's getting a little bit noisier, especially on the left side. CG it's an iterative method. It's unstable. You have a lot of stopping parameters and so on. If you do more computation, you can make it more stable, but if you speed up by twice, you get a noisier solution. If you use an iterative sketch, you speed up by something like 17 times, and you get a solution that is more accurate than CG. Okay, so this was our iterative sketch. What was the sketch dimension that I was using here? The original A has a rank of around 17,000. So if we didn't take into account more of the geometry, the structure of A, in a worst case sense, I'd have to project to dimension 17,000. We actually projected to dimension 2,000. So that's part of the reason for the speed up. And the reason that we're allowed to do that is because A is full rank, but it has very fast spectral decay. And our theory, if you go through it, will show that you can use lower sketch dimensions. Even if you have a full rank matrix, if it has fast spectral decay, it's, again, a simpler object, so we can approximate it with a lower dimension. All right, so this is a little toy, but it does give you a sense. And the method's very easy to implement because you're just sketching and solving low-dimensional least squares problems. All right, so far I've been talking purely about least squares problems. And that's sort of useful in part because, as I said, the histories of this area, a lot of sketching has been done in the numerical linear algebra world, and there least squares are sort of course, a canonical and very interesting class of problems. But in machine learning, we're interested in more than just least squares problems. And it turns out that much of what I've been talking about is not really that specific to least squares. It's useful to start with least squares because it's concrete and we can have lots of intuition about it. But let me describe this iterative sketch in more detail in a somewhat more general context now. Okay, let me just give you some pretty pictures first to give you intuition for the theorem that we're going to prove. Because the theorem is going to sort of clarify a difference between first order and second order methods. And you'll see that our method is essentially the punchline is our method has the complexity of a first-order method with close to the guarantees of a second-order method. And I'll make this precise. But let me just give you intuition. So a first-order method, what does that mean? It's an optimization method that looks only at the gradient. We're dealing with differentiable functions, in general twice differentiable functions, when I start talking about second-order methods. So for the class of problems that we're looking at, where you have an n by d data matrix, the computation of the gradient is roughly O of nd, because you end up having to do an nd matrix multiply. So that's relatively cheap. But gradient descent is well known to suffer from zigzagging problems in general. And what does that mean? It means that when you have a cost function that is somewhat ill-conditioned, ill-conditioning means in what sense is it elongated here versus steeper here, that ratio, that aspect ratio, tells us about the conditioning of the problem. Gradient descent will zigzag as a function of the condition number of the problem. And you can fix it to some extent. Nesterov's accelerated gradient descent will weaken the dependence on conditioning, but there are fundamental lower bounds that say no first-order method can be made independent of condition number. Okay, so where does Newton's method? That's a second-order method, a method that computes both gradients and Hessians and computes a Newton direction. It's much more expensive now, because you have to solve a least squares problem to compute the Newton step. And the least squares problems in our settings, again with n by d matrices, d less than n, you're going to pay nd squared. So it's a quadratic instead of a linear price in the dimension. Okay, and that really matters. If I have a problem where I have a million features, that's fairly routine these days. A million squared and a million are very different objects. Okay, so we're not just talking about constant prefactors in complexity, we're talking about dimension-dependent complexity factors. On the plus side, Newton's method is affine invariant. It's independent of conditioning. And so, at least locally, that's why we see such fast convergence rates from it. It's sort of inverting the poor conditioning of the problem by using a quadratic instead of a linear approximation. Now, our iterative sketching algorithm, what is it? What it actually is a randomized version of a Newton method. It's a randomized quasi-Newton method. And the complexity that it has, I'm suppressing log factors here to be accurate, but the complexity it has is up to log factors the same as a gradient method. Okay, but it's not a gradient method, because as we'll see, it's going to be computing elements of the Hessian. It is a quasi-Newton method, randomized. But what we'll see is that it is also condition number independent. Right? So it's a method that has the complexity of a first-order method, but it has the condition number independence of a second-order method. And that's sort of the punchline. We're going to see in practice, condition number independence is a very valuable thing in practice. All right, so let me set this up a little more precisely. Okay, the class of problems we're looking at are problems that look like f is a of x. A of x is our usual data matrix. Right? So if f is Euclidean norm, this is a least squares problem, but we can think of more general f's now. We want the f to be differentiable and so on. We'll actually assume twice differentiable because we're talking about second-order methods. An ordinary Newton step, what is it doing? It's forming a quadratic approximation. And if you have a constraint set, it's minimizing this quadratic approximation around the current iterate x of t. It's minimizing this to figure out the next iterate. Okay, so Newton's method is solving, at each step, it's solving a least squares problem where the quadratic is determined by your Hessian. Okay, so as I mentioned, our method fits into the class of quasi or approximate Newton's method. There's an enormous literature on this that I can't do justice to in a short talk. For instance, Nosedal and Wright, chapter 6 has many, many details on all sorts of different quasi-Newton methods. A number of them are, in some sense, not really second-order methods, in the sense that they never actually compute anything to do with the Hessian. They do clever things like take gradients nearby and use differences of gradients to approximate second derivatives. So that's very useful, but at some level, they're still first-order if we think about what information they're using. Prior to our work, there was also some interesting paper by Bird et al. That kind of did a stochastic quasi-Newton method in combination with a stochastic gradient method. Our method really, we're not going to approximate the gradient. It's going to be a pure stochastic Newton method. OK, so here's our method. I'm just going to rewrite the Newton steps in a slightly different way. I'm going to rewrite them in terms of the matrix square root of the Hessian. This exists because we have a convex function. We have a positive semi-definite Hessian. Now, to be fair, we're assuming that you can get your hands on this easily. That's not always the case, but there are many, many problems in machine learning where that is the case, because we have a function that's of the form f(ax). So for instance, if you have maximum likelihood with independent data, that means that f decouples, and it means that it's very easy to compute the square root of the Hessian. That's something you can get your hands on. All right, so if you did this problem brute force directly, you would get nd squared. Now, here's the iterative Newton sketch. Okay, instead of computing the exact Newton direction, we're going to left multiply this matrix with a sketch matrix S of t. Okay, so that's what we were doing at the start of the talk, but now we're doing it sequentially. You get a fresh S of t at every step, and you're sketching a new problem at every step. Okay? If you have a least squares problem, then actually the Hessian doesn't depend at all on x of t. It's time invariant. In that case, all we're doing is re-sketching the least squares problem many, many times. That's a very special case of the sketch Newton algorithm. Okay, and what's key is we preserve the gradient. We don't sketch the gradient, and that's fine. From a computational point of view, this is not what's expensive. What's expensive is the quadratic term. And if you sketch, we're going to sketch in general to a dimension that's at most d. We're going to pay a price nd to solve this update. Okay, so that's the algorithm. And so essentially, if you have a Newton solver, we're just proposing that you solve a projected form of your Newton step. You get a random Newton, quasi-Newton direction, and we'd like to prove something about the convergence of this method. Okay, so in our paper, we prove a number of theorems. As I mentioned, again, we prove theorems not for specific sketch matrices. We sort of give a meta-theorem that says that if the S's have good properties, then your algorithm will have good properties. So I'm not going to go into the details of that here. Let me just sort of assume that we're working with good S's. And good S's include many things that we know and love in practice, including things like sparse JL sketches, fast JL sketches, subset sampling sketches if you have side conditions on leverage scores. All sorts of things can be certified to be good in the sense that we need. Now, when people analyze Newton's method classically, there's sort of two branches of analysis. The sort of older style of analysis is purely local. What it sort of says is that for any function, let's say convex smooth in some sense, if you're in a local neighborhood around the optimum, then the method will behave well. So it's not really a global guarantee because it doesn't really tell you if I start anywhere, how long does it take me to get to this neighborhood, and so on. We can prove a result of that form for our method, but what I'll show you here is the different style of guarantee for Newton method. When you assume that your f is self-concordant, this includes many things that we know and love, things like log det or logarithm functions, various kinds of barrier functions are self-concordant. Then you can actually get global guarantees. So that's what I'll present here. Okay, so we're going to have a problem of this form with f being self-concordant. We have an n by d data matrix. Think of n as bigger than d. We're going to use a good sketch. And what this says is that with probability that's exponentially high in m is your sketch dimension. I'm choosing m to be proportional to d. The number of steps that you need to get an epsilon accurate solution is going to be, they're universal constants. That means they don't depend on A, they don't depend on F, they don't depend on anything in your problem. We can give you actual numerical values, such that if you take, at most, constant C2 times log 1 over epsilon steps, you will get an epsilon accurate solution. Okay? So this is a parallel to the guarantee that we have for Newton's method. except it's a randomized and lower complexity guarantee. So what have we lost? We've lost two things. Newton's method gives you a log 1 over epsilon convergence rate because it's superlinearly convergent. Our algorithm is kind of linearly, it has a mixed behavior, so in a worst case, it's dominated by this. So if you want a super accurate solution, epsilon 10 to the minus something, then Newton's perhaps is better. But I would argue in a lot of machine learning problems, you shouldn't be over-optimizing. The data is setting an intrinsic sort of noise to your problem. And if you start giving me 10 to the minus 20 bits of precision where the statistical error is at 10 to the minus 4, you're wasting your time. So I think for many regimes of epsilon, that's not a concern. Other people that I talk to, some certain style of applied mathematicians who may or may not be present in this audience, they get very concerned about the difference between a deterministic and a randomized guarantee. And they say, well, what if your algorithm fails? I'm uncertain to apply an algorithm like this. But this kind of exponential concentration, this comes from concentration of measure. We're analyzing random matrices, and we're studying how things like their spectral norms are concentrating. It's happening so fast, and the constants are very explicit, probably something like 2 and 1/8, that if you put m equals 10,000 and you compute this probability, it's much more likely that your hard drive is going to flip bits as you implement your deterministic algorithm than my randomized algorithm is going to fail. Okay? So you see sometimes people prove randomized algorithms, they say with probability 0.8 it works. That's a very different regime of guarantee than to say with probability 1 minus e to the minus m it works, when m is large. Okay, so things to understand here, just to connect this analytically back to the picture that I showed you before. Right? So this is what's known as an iteration complexity for the method. It's saying that many steps as a function of epsilon. And notice it's completely independent of problem parameters. It does not depend on conditioning. So that's the iteration complexity of this method. If we multiply it by the computational cost of each update, then we get a measure of flop complexity to compute an epsilon accurate solution. So let's compute flop complexities, computational costs, for a bunch of other methods. Okay, so gradient descent, as I've said, if we apply it to a problem where we have some kinds of strong convexity conditions, so we have a problem with a condition number kappa that's not infinite, the total cost for an epsilon accurate solution is kappa nd log 1 over epsilon. This method is nd log 1 over epsilon. So the difference is it's condition number independent. And you might think, well, who cares? Kappa's a constant. But that's not the right way to think about it. When you study sequences of problems, the conditioning can diverge as you scale to larger and larger problems. The fact that you do not depend on kappa can mean a lot in practice. And I'll show you an example in a moment. Nesterov's accelerated gradient descent, as I mentioned, is a clever method, basically a momentum method that drops kappa to square root kappa, but that's unimprovable over the class of first order methods. If you only look at gradients, you cannot have a faster algorithm than that. Newton's method, as I mentioned, is condition number independent, much faster convergence, log 1 over epsilon, but it has a quadratic price in d. Okay? So I'm not claiming that this method is better than all these other methods. I don't think that's the right way to formalize the problem. The right way to think is they give you different points, different sort of trade-offs of different complexity parameters. And you have to look at your problem and say how big are n and d and kappa and epsilon, and we'll see different regimes in which one algorithm is better than another. That being said, there are plenty of regimes where we found that this method is very competitive. So let me just give you a couple of examples. Okay, so here we're solving a sort of medium-sized logistic regression problem. It has 5,000 features, a sample size of 500,000. What I'm showing you, just to keep the plots relatively clean, is I'm showing you Newton, gradient step, and Newton sketch. I'm not showing you iteration numbers because that doesn't make sense. Gradient iterations are much faster. Newton iterations are slower. I'm showing you wall clock time. That's what matters. It's all on a common machine. And this is a problem where I've sort of synthetically constructed it, so the features, meaning the columns of the data matrix, are roughly uncorrelated. What you see here is that gradient descent is a very good method. It's actually certainly better than the Newton sketch originally, but both are pretty good methods. You can see Newton is suffering because you're paying a d squared price. You're paying 5,000 squared per step, and that's going to hurt you in wall clock time. Right? So Newton's ultimately will be faster converging. These are linear, but we're not anywhere near to the quadratically convergent regime here. All right, so this is a problem where I would say gradient descent is probably the best. It's a somewhat simpler algorithm than a Newton sketch. But of course, in practice, do you believe that when we solve large-scale logistic regression problems, do we have uncorrelated features? What's a practical example? People build spam filters. Your Gmail inbox has a spam filter, luckily for you, given that something like 99% of email on the internet these days is spam and you don't see it. Right? What it's doing, it's essentially constructing things like logistic regressions or other classifiers using large numbers of features collected from your email. But those features, when you collect them, things like is Viagra in the subject line or not, or strange attachments, these are obviously highly correlated. When you get spam, many of these features are going to be on. So a more generic feature you expect is when you do logistic regression with correlated features. And what correlated features mean is that your condition number now is getting worse. And so you can see immediately that the theory is not conservative. Gradient descent starts to behave in a rather funny way here because this is a relatively ill-conditioned problem. Newton's method is behaving exactly the same because Newton's method is condition number invariant, but it's still expensive. The Newton sketch is behaving pretty much exactly the same way. You see linear convergence. It's not being affected. It's not being slowed down by the conditioning. Okay, so that's the benefit here, is that it has complexity of a first-order method with condition number invariance. As I mentioned, it's a randomized algorithm. So actually what you're seeing here are sort of 10 trials. And you can see it's tightly concentrated. Right? Our theory says that with very high probability, it's going to go close to the optimal answer. And you can see over 10 trials, you're not seeing large fluctuations. That's showing us a concentration of measure in action. Okay, so I think the point to understand is that in practice, you just need to understand what kind of problem am I working with. And you, of course, can get a sense of the conditioning of your problem. If it's very poorly conditioned, if it's well conditioned, then I think gradient descent first-order methods are great. But this method is definitely competitive for problems that are a little more ill-conditioned. Let me give you another application. Right, so essentially, because Newton's method is a workhorse, people use Newton's method all the time in many different computations. We use it not just for nonlinear optimization, we use it more generally for fixed point computation. Another place we use it is in the context of interior point methods for solving conic programs. Linear programming is a special case, but probably the most important one. Right, so a linear program is just trying to minimize in standard form, let's say we minimize a linear function over a set of linear inequality constraints. So my data matrix A is here again. I've been assuming throughout that n is bigger than d. For a given LP, that may or not may make sense. In this context, n is the number of constraints in your LP, the number of inequalities. D is the dimension. But LPs can all be dualized, and that would flip the roles of n and d, so there's not really any loss of generality in assuming that n is bigger than d. You can always convert it to one of these standard forms. Okay, so what an interior point method does is it seems a little weird because it makes your problem harder. And so what it does is it takes the constraints that are defined by this set of inequalities, and it puts a logarithmic barrier function on them. Right? So this is a function that diverges. It's going to penalize you infinitely as you approach the boundary, as you get close to violating the constraint. Right, so that's why it's called an interior point method, because it's working inside the constraint set always, and you're going to allow it to approach the boundary. Now, the way that you allow it to approach the boundary is you have a parameter mu that essentially controls the balance between how much you respect the original cost function and how much you're respecting the barrier. And you have a particular sequence of changing mu so that you approach the boundary in the right way. All right, so those details aside, what people are doing in interior point methods, at least a class of them, is you're taking Newton steps on a sequence of these problems. But the Newton steps, again, are expensive in general. So you can sketch the Newton step, and you get a sketched interior point method. And what can we say about such a method? So the way to think about interior point methods is you start at some interior point, and then you're going to follow a sequence of steps based on taking Newton steps until you approach the boundary. As you take these steps, you're adjusting this parameter mu as well, so that you're being allowed to approach the boundary. When we sketch it, we're taking random steps based on a sketched version of the barrier. So it's kind of interesting. You can think of the barrier from a physics point of view. It's an energy barrier in some sense. We're not enforcing that barrier exactly, but we're enforcing a randomized version of that energy barrier. So we get a randomized algorithm. We want to prove how does this randomized algorithm behave? How quickly does it converge to the optimum as well? All right, so if you plug in the Newton sketch, what you can show is that we can solve each of the Newton steps in O of nd time. Okay, so that means that what we should expect to see out of our solvers, if we apply them to sequences of problems where n and d grow, we should see scalings that are linear in both n and d. A classical interior point method will be quadratic in one of them. Let's say quadratic in the smaller one. It will behave quadratically as d squared. Okay, so here we've applied it to problems and compared to CPLEX. CPLEX is a commercial solver for LP solving. It's kind of weird because it's not really one algorithm. It's a great piece of engineering that has millions of algorithms and sort of, for a given instance, massages it and tries to figure out what is the best algorithm for this problem. So this method will not beat CPLEX if you give it highly structured problems where CPLEX can play some clever tricks. These are relatively unstructured problems. I think what's happening with CPLEX is it's being sort of forcing it to use its interior point method. And what you see is, as a scaling with D, CPLEX is a quadratic scaling. And consistent with the theory, our solver is a linear scaling. So again, this is a particular class of LPs. But for those of you who know of CPLEX, CPLEX is not easy to beat. And this is not an expensive algorithm to implement. Essentially, you just take an interior point solver and you sketch, and then you do an approximate Newton step. That's pretty easy to change. And if you can see gains like that, then why not? That would be my take from it. Okay, so just to wrap up, this whole area of big data or high-dimensional data, I think it's got lots of challenges and opportunities, both within statistics and optimization. I think there's been a lot of hype about big data and so on, which is kind of annoying. But at the same time, I think there are intellectually substantive issues that concern big data, and I think many of them are of an optimization, algorithmic, and statistical nature. So I think that part of it is exciting. I think optimization, so what we've seen in optimization is sort of renewed interest in very large-scale problems. We've seen a lot more interest in first-order methods because for many large-scale problems, first-order methods is all we can do. I think this is interesting because it's saying that you can do randomized second-order methods for large-scale problems. If you do it in the right way, you have complexity that's basically like a first-order method. I think the intersection with statistics and machine learning is interesting because it means that certainly approximate answers are always okay. As I've said, in fact, you should be computing relatively approximate answers. If you are optimizing to machine precision, you are most likely wasting your time because your data is noisy and your models are noisy. So you're just optimizing different forms of noise in your data or your model, and it's not useful use of computation. That's a useful perspective to take here because we're giving you randomized algorithms. So they are giving us approximate answers, but we do have good control on them, right? These are not heuristics. These are methods that you can say precisely what you need to do to get a certain level of accuracy. Since we've posted this, a number of other people have done interesting related pieces of work about randomized iterative methods. Mike Mahoney and some of his colleagues have looked at subsampling forms of Newton's sketch and proved a number of interesting things. Peter Richterich at Edinburgh has also been working in this general space. So there's sort of an evolving area at this kind of interface, and I think it's quite an exciting time to be here. So a couple of papers and preprints, and I'm happy to take any questions that people might have.